If you're interested in the foundation of quantum mechanics, you might have heard about quantum logic. The idea that quantum mechanics is so special and so different that it requires departures from the rules of classical logic, and therefore you need this quantum logic that works totally differently. Personally, I think that quantum logic really exemplifies the state of utter confusion that we are in for the foundation of quantum mechanics. So it's I decided to make a video about it. So the short point for those that can only watch 30-second videos is that the arguments giving to demonstrate that quantum mechanics requires a departure from classical logic actually do not work. They are basically based on misleading assumptions, and you can in fact use a similar misleading argument to show that classical mechanics does not follow classical logic. Now, there exists a mathematical structure called quantum logic that exists. You can prove theorems and you can do stuff with it, but it's not really particular to quantum mechanics, and it's not really a logic in the sense that it doesn't really have all the statements that we require to do experimental physics in the context of quantum mechanics. So that's the short thing, and if that's good enough for you, you learn something. Now, you shouldn't really take my word for it. You should actually go in the details and convince yourself whether I'm saying something true or not. I've also linked the paper in which me, Andrea Dofredi, and Cristina Idala show some of these arguments in more details. And essentially the video is gonna go through those arguments and give you some explanation. The video is divided in two parts. The first one is really about these logical arguments that motivate quantum logic, and those are sort of law on math that can be followed, and we're gonna debunk those and show that you can make similar misleading argument for classical mechanics as well. And then the second part is that it's more mathematically intense. So we're actually going to see what this quantum logic, this mathematical structure is, and this will require a little bit of math that almost all physicists have never seen, and I don't even know if all mathematicians have seen. It's order theory and lattices. It's really beautiful math, so I'll try to give a nice introduction to it so that you can actually follow. But we're gonna go through these details and really understand what this structure is about and show that it's not really quantum and it's not real logic. So this is probably going to be a longer video, so let's start. As I said, the first thing that we want to do is go through the arguments that are given to show that quantum mechanics does not follow classical logic. And I'll try to represent these arguments as best as I can. But before doing that, we want to do a review of classical logic itself, of logic and the operation, so that we have a baseline on which to discuss. So there are three symbols that we want to review. The first one is the negation, that it's represented with this symbol, which is called negation. And so the idea is that if we have a statement, there is a bottle on the table. The negation is the statement that is true only if the original statement is false, and it's false whenever the original statement is true. And we represent here with the truth table here. So you see that whenever P is true, negation of P is false, and whenever P is false, not P is true. The second operation is the conjunction, the logical AND, that takes two statements and returns the statement that it's true if and only if both original statements are true. So if I have the statement there is a bottle on the table and there is a glass on the table, then the conjunction of the two is that there is a glass and a bottle on the table. The third operation is the disjunction, the logical OR, which is false if and only if the two original statements are false. So if we have the two statements that there is a bottle on the table, and then we do the disjunction with there is a glass on the table, we get the statement there is a glass or a bottle on the table. Okay, the last thing that we want to review is the distributive law, that basically tells us that the ends and the or distribute in the same way that the addition and the multiplication distribute. So for example, if I have a statement, I have this expression, I will eat chicken and I will eat potatoes or I will eat green beans, this overall statement is equivalent to the statement I will eat chicken and I will eat potatoes, or I will eat chicken and I will eat green beans. Right? So distributive law is something that we use in classical logic all the time, and this is one of the things that people argue that is not valid in quantum mechanics. So let's see how the argument works. Is we are working in the context of spin measurements, and so the main idea is that whenever we measure spin in one direction, we always find it either aligned in that direction or aligned in the opposite direction. So if we have three statements, the electron has x spin up, which would basically mean that the spin would be oriented in this direction. And then we have the statement the electron has y spin up, which means it's oriented in this direction, or the statement R that the electron is y spin down, so it's oriented in this direction. We have these following two conditions. As I said, whenever we measure spin in the y direction, it is either up or down, so the statement Q or R is always true, because either one is true or the other one is true. But it's also true that if we prepare spin in one direction, we don't prepare it in another direction. So if we say P and Q or P and R, it's false because either it's in one direction or it's in the other direction. And so if we have these two premises, so suppose that P is equal to true, so that we really prepared spin in the x direction. Then we have P that is true and Q or R, but we said the Q or R is true. So we have true, and this is equal to true. On the other side, though, we have P and Q, and we know that P and Q is false, and P and R is also false. So we have false or false. This is going to be equal to false. So the distributive law doesn't hold anymore because one side evaluates to true while the other side evaluates to false. So quantum mechanics violate distributivity. Okay, the idea is that we can do something similar, a similar setup, also in classical mechanics. So for example, consider the following scenario. We have a ball that is placed at position P above a hatch. And when the hatch opens, the ball will start jumping around and will land either in position Q or position R. And let's say that due to the symmetry, you will have equal probability of going in one position or the other position. And we can say that the ball must land either on Q or R, so Q or R must be true. But it's also true that the ball cannot be in two places at once. So P and Q and P and R are false. So either it's here or it's here. It can't be in both places. So now we can do the same evaluation. Suppose that P is equal to true. Then this is true. Q or R we said is true. So true and true gives us true. But on the other side, we have P and Q, which is equal to false, and P and R, which is equal to false. False or false equal false. And so we conclude the classical mechanics violates distributivity. And so it needs another type of logic that is not classical logic. Now, of course, you're probably going to object and say, wait a minute, there is something fishy about the argument. And so what is exactly that it's fishy about the argument? Is that we need to take time into account. Right? So we have two moments where the proposition can be evaluated. We have a proposition that it's on the preparation, and we qualify those with an I as an input. And then we have different proposition, actually the same proposition evaluated at different time, that we can indicate with O because it's what happens after the measurement. So we have 6 propositions and not 3. So if we say that the spin in the y direction is either up or down after a y measurement, we are saying that QO or RO is true, but this does not necessarily mean that QI or RI is true. In fact, if we prepared in the x direction, QI or RI are going to be false. So the fact that the disjunction between these two is true doesn't mean that the disjunction over these two is true. Moreover, there is no incompatibility between the x direction before the measurement and the y direction after the measurement. So if we say Pi and QO, then this can be true if we prepared x up and then we later measured y up. But of course, PO and QO, that is always false because at the same time we can't have the direction of spin is different in the same moment. So if we rewrite our expression, taking care of whether the statements are before the measurement or after the measurement, then distributivity is not violated. So we have prepared a PI, so PI is true, and after the measurement QO or RO is true, and so we have true and true is fine. But then also we have that PI and QO is true because we prepared, well, could be true because we prepared PI, and so these PIs are going to be true. And then either we are going to measure QO or we are going to measure RO. So one of these two statements are going to be true. And then if one of these two statements is going to be true, then the disjunction between the two is going to be true, and therefore distributivity is not violated. So you see, it's just it's kind of a trick that the setup is a little bit confusing, that makes you think that something different is happening, but then when you go through the detail, everything is fine. There is nothing different. Another claim they use to justify quantum logic is that the disjunction in quantum mechanics works differently. So the disjunction classically, if Q or R is true, then either Q must be true or R must be true. So if the statement is true if and only if one of the two elements is true. And the idea is that in quantum mechanics, this doesn't happen. So for example, again, the idea is that whenever we measure spin in the y direction, it is either up or down. So Q or R is always going to be true, but this is even true if we prepared spin up, if we prepared P. So if P is equal to true, then Q and R are false, even though Q or R are true. So Q or R are true because we always measure either spin up or spin down, even if we didn't prepare spin up and we didn't prepare spin down. So disjunction works differently in quantum mechanics. And again, if we go back to our classical example, we can make something similar. We can say the ball must land either in Q or in R, so Q or R is true. And this is even true even if we prepare the ball in P. Even if we prepare the ball in T, when we measure, we're going to have either Q or R. So if P is equal to true, then of course we didn't prepare Q or R, therefore these are false. But Q or R is still going to be true, and therefore, again, disjunctions work differently in classical mechanics. And again, this is something similar to what happened before. So as before, we need to take time into account. The fact that the spin, y spin is either up or down after the measurement tells us nothing of what happens in other cases. In fact, we can, set up other cases in which other two directions, one of them has to be true. So for example, suppose that after the measurement, if we measure Q up, we do nothing. We just leave it the spin up as it is. But if we measure spin down, we rotate the spin by 90 degrees and we put it in the x direction. So we have created a situation after the rotation that either Q or P are true, right? In the same way that after the measurement, either Q or R were true. But the fact that Q or P are true here, it tells us nothing about what's happening here or what's happening before. So it does not follow that we must always have X spin up or Y spin up, because that happens to be the case after our rotation. So in a more general sense, the disjunction is working as it's supposed to. The only thing is that we have constraints. So we can prepare spin in any direction and in only one direction. It's just that after the y measurement, we know that the spin must be either up or down, because those are the only possible outputs of the measurement device. So the measurement device is introducing a constraint such that after the constraint, either you have spin up or you have spin down, and all the other states are excluded. And this is similar in the dropping ball example. We have a constraint on the final state of the system that it's either in Q or R. But this is not a property of the system itself as a sort of a general property of the system. It's a property of the constraint that is put on the system at a particular time. And so if we know, and if we are careful in putting in constraints, then we understand that there is no problem in the logic. There is another, a little bit more subtle claim that quantum mechanics fails to follow classical logic that has to do with the uncertainty principle. So let's look at that as well. So suppose that we have here a phase space, so position and momentum, and we have two cells of a phase space, each of them that are big h bar over 4, which means that if we put them together, this whole region is going to be h bar over 2. And so we're going to have two statements. One, the statement Q, that the state of the particle is in A. The other one, the statement R, is that the state of the particle is in B. And then we take the disjunction, and the disjunction is going to tell us that the state of the particle is in the union, is in the overall region. And so the claim is that Q or R can be true, because of the uncertainty principle, we can fit a particle within those bounds, but we cannot fit a whole particle either in A or in B. Therefore, Q and R are false. So it can be that Q or R is true, but if it's true, still Q and R, the disjunction elements, are false. And therefore, we have another situation in which the disjunction works differently than in classical logic, and so quantum mechanics is different, is special, and needs something different. And the idea is that, again, we can make a classical analog of this example. So suppose we're taking the sun, we consider the sun, and the radius of the sun is about 700,000 kilometers. So we can imagine a region in space that is 1,400,000 kilometers squared, and we divide the region into two, A and B, right? Such that the whole region can contain the sun, while each half a region is too small to contain the sun. And so we have three statements here. We say that the sun is in region A, right? The sun is in region B, or the disjunction between the two, the sun is in the region A union B, so it's in the whole region. So again, we can say that the statement Q or R can be true because the sun can fit in the whole thing, but because of the size of the sun can't fit in A, can't fit in B, so Q and R, or both of them, are false. And so again, the disjunction works different in classical mechanics, and classical mechanics does not follow classical logic, and we need something new and different. And of course, this does not make sense, and the issue here is that objects have an extension. And so when I just say the sun is in the region A is a misleading statement, because I could be saying two different things. I could say the whole sun is in the region, or the center of the sun is in the region, and these are two different statements. So if I say that the center of the sun is in region A, or the center of the sun is in region B, then the center of the run, the disjunction between the two statements, is exactly that the center of the sun is in region A union B. Because if one of these two statements is true, then of course this one has to be true. But if I take the other case, that the whole sun is in region A, or the whole sun is in region B, then this is not the same as saying that the whole sun is in region A union B, because the whole sun can be in A union B, but only partly in A, partly in B. So this can be true, this statement can be true, even if both of these are false, but the issue is that this statement is not the disjunction of these two statements, because there are other cases. And distributions are objects that, like the sun, have an extension. So suppose now we take a classical distribution on phase space, so it's a row of x and p, and you can imagine this either is a statistical distribution, so you really have a bunch of particles spread out, or a probabilistic distribution. You have one particle with a probability that is going around. We again say that the state of the particle is in A is an ambiguous statement, because we could say two things. We could say that the center of mass is in A, right? And so we do the expectation value of x, we do the expectation value of p, and this point is in A. And then it's true that the disjunction of the two elements is that the center of mass is in the union of the two regions, right? And this is true. But when we are discussing uncertainty, right, with the uncertainty principle, we're not really looking at the center of mass of the distribution. We're really looking at the standard deviation. So what we could also mean by the state of a particle is in A is one standard deviation of the distribution is in A. So like a whole block of the distribution is all in A. And so what we are doing is that we are taking a box, essentially, we've centered at the center of a mass, so average x and average p, and we take it that it's the size on the x is one standard deviation and the size on the p is one standard deviation. So now the statement is that this whole box is inside A. And now in this case, since we have an extension, it's no longer true that when we do the disjunction between the statement in A and the statement in B, so R, Q, and R, this is not going to be the same as saying that one standard deviation of the distribution is in the union of the region. Because we can have that half sigma is in A, half sigma is in B. So it is true that the one standard deviation is inside the whole region, while it's never wholly in region A or region B. So again, the issue here is not that quantum mechanics is different, is that the logic that how these things work for distribution is different than what happens for objects that are really like point. And so the disjunction does not always map to the union of regions. That's really the problem. And this has nothing to do with quantum mechanics. It's just it has to do with objects having extensions, and probability distribution have an extension. In fact, it is exactly what happens in quantum mechanics, because it works the same, just we have to replace what their definition of state is. And then the other thing that we need to do is that when we calculate the average and the standard deviation, we just have to use the quantum expectation way of doing things with the trace of the operators and so on. And that's it. Everything else just works the same. So the conclusion is that none of the arguments that we presented for quantum logic are actually valid. They're essentially based on misleading premises. And if you take into account time, if you take into account constraints and the fact that distributions have an extent, then all these problems are resolved. And the same problems you can use to create misleading argument for classical mechanics. And so really classical mechanics and quantum mechanics at the logical level works exactly in the same way. So this concludes this more sort of conceptual part of the video, and now we're going to go into more of the mathematics of quantum logic. As I said in the introduction, there is a mathematical structure called quantum logic, and the issue is that it's not really quantum in the sense that other structures, other physical theory will have that same structure, and in my opinion it's not really a logic, at least it doesn't play a role of a logic structure in the physical theory. But to be able to really understand why some people call it quantum logic, we have to go and look at the mathematical details a little bit more. And in particular, we have to go and learn a little bit about topics that are typically not taught in standard physics, but sometimes not even in a math curriculum. We have to look a little bit about order theory and lattices in particular. And so we're gonna have to go through a fair amount of material, and we basically just get an introduction on the topic. And it's really an interesting, order theory, it's really an interesting, fascinating topic, because once you start thinking in terms of those structures, you actually find them everywhere. So it might be interesting anyway. So let's start. So if you remember, when we introduced the disjunction, the logical OR, we defined it as a statement that is false if and only if both statements are false. But then, when we were talking about the disjunction in the context of quantum mechanics, we were saying that the disjunction there was true even if none of the original statement was true. But then, this is a problem because by definition, it wouldn't be the disjunction as we defined it, right? So this does not make so much sense unless you realize that what happens is that you're not really talking about the disjunction, but you're really talking about some sort of generalization. And this is something that happens in mathematics a lot. Mathematicians like to generalize concepts, which means changing the underlying definition, but oftentimes they leave the terminology the same. So, for example, in topology, you talk about open sets because they are the generalization of the open intervals of the real line. But then what happens in topology is that sets can be both open and closed, which of course you can have both an interval on the real line that is both open and closed, right? So basically you are still using these terms, but these terms have acquired a different meaning and therefore they even have different properties of what you originally thought that they would have. And this is why, if you really want to understand things well, in these cases, you have to know the math very well so that you can understand whether the generalization that the mathematicians are doing is appropriate in the physics, and if it's appropriate, what it is that you're generalizing and how. So this is what we have to do here today. Okay, so what are these structures that we are going to talk about? We are going to talk about order theoretic structure. In particular, we have to define what a partial order is. So given a set, a partial order is a binary operation, so an operation that takes two elements of the set and returns true or false. In particular, this operation has to have these three properties. It has to be reflexive, so A is less than or equal to A. It has to be antisymmetric, so if A is less than or equal to B and B is less than or equal to A, then A is equal to B. And it has to be transitive, so if A is less than or equal to B and B is less than or equal to C, then A is less than or equal to C. If these properties are satisfied, then this is called a partial order. And a partially ordered set, also called a poset, is a tuple of a set together with a partial order. So let's give us an example of one of these objects. Let's take a collection of subsets, of a bigger set with the operation set inclusion. And we can see that set inclusion is a partial order because it satisfies these three axioms. It is reflexive because a subset is a subset of itself. Is antisymmetric because if A is a subset of B and B is a subset of A, then A is the same set as B. And it's transitive because if A is a subset of B and B is a subset of C, then A is a subset of C. We can give an example, a concrete example. So let's consider all the possible subset of A, B, and C. And here we draw what is called a Hasse diagram, which is a diagram that allows us to visualize partially ordered set with finitely many elements. So we're going to have here the empty set. Here we have the sets with one element. And there is a line signifying that the empty set is a subset of the set with only A and is a subset of the set with only B and is a subset of the set with only C. Then we're going to have the set with two elements, so AB, AC, and BC. And again, if the subset with only A is a subset of the set with A and B. And of course, the empty set is also a subset of A and B because it is a subset of A. So by transitivity, we can see that, we can see essentially all the relationship. And of course, on top, we have the full set with A, B, and C. There is a superset of both AB, AC, and BC. So this is a way to visualize the fact that all the possible subset of A, B, and C form a partial order, is a poset, and we can see here all the possible relationships. We can see some other example. This is the set of adjacent vertices of a square. So we have the empty set with no vertices, the set with only one vertex, A, B, C, and D, and then the sets with two vertices. And of course, we should take only the ones that are adjacent. So we have AB, BC, CD, DA, but we do not have AC and we don't have BD. And then we have the set with three vertices, ABC, BCD, CDA, and DAB, and then the set with all four vertices. Okay, so this is an example that we can give of a partial order set. And you might ask, why are we interested in partial set, order set at all? We said that we are interested in logic, right? Well, the idea is that a set of logical statements with imply is a poset, right? So if a poset satisfies these three axioms. So if the statement A, as the statement A is going to imply itself, if the statement A implies B and B implies A, then A is equal to B. And if A implies B and B implies C, then A implies C. Right? So the idea is that a set of logical statements with implies is a poset. That's why we're interested in poset. And here again we can give an example in terms of the example that we used to introduce the operation. So the statement that there is a glass and a bottle on the table implies that there is a bottle on the table, and it also implies that there is a glass on the table. And none of these imply each other. And both of these statements imply that there is actually a table. And we can also see an example with the type of statement that we were using in quantum mechanics. I prepared x plus and measure y plus implies that I measure y plus, and it also implies that I prepared x plus. As I said before, once you learn about this structure, you kind of see that they are ubiquitous. And so, for example, you can try and show and convince yourself that the set of integers or the real numbers with less than or equal is a partial order, that the set of character strings together with the operation is a substring of is also a poset. You can go and see that it satisfies those axioms. In fact, these type of structures are very common in theoretical computer science, so that there are a lot of use of posets there to model computation. And you can also see that at a physical level, a set of physical objects with the operation is part of is also a poset. So as I said, this is actually fairly basic structure once you know how to look for them. Now, we're not only interested in posets, so we are interested in a particular type of posets that is called a lattice. Now, a lattice is a poset, it's a partially ordered set, such that for any two elements, A and B, there exists a list upper bound that is called a join, and it's noted A join B. And there exists a greatest lower bound called meet, and noted A meet B. And note that the join and the meet are the same symbols that we use for disjunction and conjunction, so there's going to be a relationship there. Now, the least upper bound is essentially the lowest of all the elements that are bigger than A and B. And for example, we can see here that this is not a lattice, because if we take B and C, there are two elements, D and E, that are bigger than both B and C, but neither of them is smaller than the other. So there isn't a least upper bound. We have two upper bounds, but there is no least. So there isn't an element that is the smallest. In this case, instead, if we take B and C, then we see that E is bigger than B and C, but also H is bigger than B and C. But H is bigger than A, so A is the least upper bound of B and C, and so this is going to be the join. And if you go and look all the elements, they always have a least upper bound and a greatest lower bound, and therefore this actually is a lattice. It satisfies the axiom of a lattice. Moreover, a bounded lattice is a lattice where there exists a greater element, which is called top, we've indicated with this T, and a least element called the bottom, which is indicated with this upside down T. So if we go back to our original examples of sets, we find that collection of sets form lattices if they have inside the sets, inside the collection of sets, you have all the unions and all the intersections. So for example, this has all the possible subset on A and B, and this is a lattice. You can see that it has the same order structure than this. And again, you can see that A and B, the join is actually the union, and A and B, the meet of A and B, is the intersection, which is going to be the empty set. We can also see that this set of a subset is not a lattice, precisely because it's going to lack some of the sets. It's going to lack some intersection and some unions. In particular, we can say that for A and C, ABC is an upper bound, but also CDA is an upper bound. So these two elements are bigger than both elements. But you can see that none of them is bigger than the other, and therefore we don't have a join, and this is not a lattice. And you can see that this is exactly the case because we're missing the set that contains only A and C, which would be the union. So the fact that we're missing the union means that this set of subset is not a lattice. Okay, so again, the real reason why we're interested in this structure is because we're interested in statements and logical structures. And the idea is really that a complete collection of statements does form a bounded lattice. And the idea then that the join is not really a disjunction, but so it's not really the statement that it's false only if both statements are false, but you should see it as the most restrictive statements implied by both statements A and B. And the meet is not the conjunction, but is the most general statement that implies both statements A and B. So these are really the definitions that correspond to the join and meet. So for example, here we have a set of 5 statements, and so A implies B, A implies C, A implies D, and we also know that B implies E, C implies E, and D implies E. Now, what happens here then, if any statement is true, implies that all the statements that are above are also true, because now it's an implication that gives us the order. So suppose that B is true, right? So if B is true, then E is true as well. But E is the join of C and D. So if B is true, then the join of C and D is true. But the fact that B implies E does not mean that B implies C or B implies C. So what happens is that this can be true, which implies that this is true, but both C and D can be false. So we can have the case that E is true, that is C join D is true, but C is false and D is false. So in this case, I wouldn't really say that there is a violation of disjunction. I would simply say that the join is not necessarily a disjunction, and it's a disjunction just in particular cases. At least I think it's more clear, and it tells exactly what is happening. Now, again, you could go and look at the 3 other structures that we talked before and try to see whether they're lattices or not, whether they're bounded lattices or not. And I think like doing this sort of exercise helps you understand these structures a little bit better. Now, the third structure that we are interested in are Boolean algebras. Boolean algebras are important to us because they are basically classical logic. The Boolean algebra is going to be a type of lattice, and we first need to define what a distributive lattice is. And a distributive lattice is a lattice where the join and meet are distributive. As we remember, that's what we saw. That basically says that the join of meets can be expressed as a meet of joins. And then we also have the notion of a complemented lattice, which is a bounded lattice with a complement operation, such that A join complement A is equal to the top, and A meet complement of A is equal to the bottom. And now to understand what these operations are, we can reread them by understanding this as the disjunction, this as a conjunction, and this as the negation. So we have that A or not A is equal to true. A and not A is equal to false, right? These are just identities in the Boolean algebra. And so what happens that in terms of order theory, a Boolean algebra is exactly a complemented distributive lattice. And in this case, then the join becomes the familiar disjunction, the familiar or, the meet becomes the and the complement becomes the negation, becomes the not. Okay, so this is the connection. A Boolean algebra is essentially classical logic. We have identified it with the lattice, but the issue is that not all logic are Boolean algebra, but many of them are lattices. So by studying lattices, we can also study other types of logics. For example, the Eigen algebra, which is the algebra used in intuitionist logic when you worry about proof or you worry about computation, if something can actually be computed. This algebra is not Boolean, but it's still a lattice, and therefore, when you're studying different type of lattices, you're also studying different types of logic. But the converse is not strictly true. It's not that whenever you have a lattice, you have a logic of some kind. Okay, so we saw all the examples that we saw were about both sets and statements and logic, and this is not a coincidence because we are actually interested in the relationship between these two. And the idea is that a collection of subsets can also form a Boolean algebra if the set of subset has all the union, the intersections, and the complements. And in that case, then the union is the join, intersection is the meet, and the set complement is the complement of the Boolean algebra. And the link between the two works as follows. So consider a scientific statement like the mass of the electron is 500 plus or minus 50 kilo electron volt. Like this follows this pattern. There is an element x, the mass of the electron, and we are claiming that it's within a set of possible values, an interval of a real line. The same thing goes for the second example. We have the Earth-Moon distance, which again is something that is going to be bound within a particular set, a particular interval of the real line. Even in this simple case where we say there are 6 flavors of quark, you can say that there is an x, the flavors of quark, and we're saying that that x is inside the set with only one element, 6. So this pattern is actually, essentially, it's always there, and we can always think about these statements, these measurements, as saying that something, the object that we're describing, is in a subset of all the possible ways that the object can be, and this is a subset of x that is the set of all the possible ways that it can be. And so this link between set theory and the statement is going to be important to us, and we're going to see it later as well. Okay, so to recap, we're seeing that logical structure can be understood as order theoretic structure, in particular that can be understood as lattices, and the join and the meet are generalization of the disjunction and the conjunction in the context of lattices. We saw that the Boolean algebra follow the standard rule of classical logic that define them, and they can be represented as collections of sets where then the logical operation become the set operation. They become the union, the intersection, and the complement. And then we saw that there are other types of logic that are also lattices, and for example, the Artin algebra in the context of intuitions logics, and that's why in many cases, studying different lattices means studying different logic. And so now we have the context in which we can now finally understand what quantum logic, what this mathematical structure called quantum logic actually is. The starting observation of quantum logic is that in the formal treatment of quantum mechanics, the output of a measurement is an eigenstate of a Hermitian operator, right? So that's what the math tells us. And so the idea is that the final state of a measurement is an element of a closed subspace U, and therefore the only testable statements are of the form x is in U, where the U is one of these closed subspaces, right? So that's the idea. And here closed means that the subspace contains all its limit points, or equivalently it's the complement of an open set, so it's topologically closed. So then the idea, if this is the case, is that it makes sense to look at the set of all closed subspaces and see what that looks like. So let's look first at the real vector space case. So the complex vector space, it's very similar, but we can get a better intuition in the real case. So let's look at the set of closed subspaces in R3 and see what these are. So the set with only the zero vector is a closed subspace because any linear combination of the zero vector is going to give you the zero vector, and therefore you're staying in the same subspace. Every line that passes through the origin is also a one-dimensional closed subspace, because if you take any vector that lies on the line and you make a linear combination, you're always going to get another vector that is on the line. So that's a subspace. Every plane that passes through the origin is a two-dimensional closed subspace, because if you take two vectors that are on the plane, you make any type of linear combination, you're always going to remain in a plane. And then the whole space is a three-dimensional closed subspace because any linear combination in xyz is always going to give us a vector in xyz. And so these are the only things that are there. There are no more subspaces. So that's basically it. So it's not very complicated to visualize. Now, in a complex Hilbert subspace, things work exactly the same way, except that they are complex. So therefore, we don't think about lines that pass through the origin, but complex plane that pass through the origin. And then the Hilbert space in general can be infinite dimensional, but it turns out that we don't really even need to look at the infinite dimensional case. We can just stay finite dimensional and understand it from there. Okay, so let's look at the set of closed subspaces inside a complex Hilbert space. So let's write this script L as the set of all possible closed subspaces. Each subspace is a subset of the whole Hilbert space, so L is a collection of subsets which can be ordered by inclusion, right? So a line may or not be contained in a plane, right? So it's you can say whether it's all inside it or not all inside. And so a set of closed subspace together with set inclusion is a partially ordered set. So we can finally start to use what we have seen there for 20 minutes. We can also see that the whole space H is a closed subspace, so it's inside L, and that all subspaces are subsets of H, right? So in the same way that R3 contained all the lines and all the planes. Therefore, the whole space is the greatest element. It's the top. The zero vector by itself forms a closed subspace, and all subspaces contain the zero vector, because remember, we're only interested in lines and planes that went through the origin, and so they of course contain the origin. And so the zero vector as a set is the smallest subspace, and therefore it's our bottom. So we have bounds on the poset. Now, suppose that we take two closed subspace A and B. Now, if we take the intersection, that the intersection is a closed subspace, and it's going to be the largest closed subspace contained by both, right? So for example, if we have two planes that pass through the origin, if they intersect, they're going to intersect and make a line, and the line is a closed subspace. And so what we have here is that the intersection then, it's the meet operation. So the intersection of A and B is actually, in terms of the poset, it's the meet. It's the greatest lower bound. Now, if we take the union, however, of two subspaces, this is not a closed subspace because there might be things that are in the linear span that are not in the subspace. So if we take the union of two lines that pass through the origin, of course we don't get the whole plane, we just get two lines, and therefore that's not a closed subspace. But if we take the closed linear span of two subspaces, this is by definition the smallest space, the smallest subspace that contains both. And so that's the join. So we have the union of A and B is not the join, but the closed span of A union B, that's the join. And since again we can see that the join is not the union, we already know that this is not going to be a Boolean algebra. But we found that the set of closed subspaces is a lattice because it has the joins of the meet, and it's also a bounded lattice because it has a top and the bottom. But it's not going to be a Boolean algebra. So now we can see the failure of disjunction in this more precise setting. So if you remember, we had that Q or R equals true does not imply that Q is true or that R is true, right? But let's translate this into lattice operations. What we really have is that Q or R is basically the statement X is in the closed span of Q and R. So if this is true, that does not necessarily mean that X is in Q or that X is in R. because the span of two subspaces, as we said, if we take two lines, that's not a closed subspaces. We're going to have to get the whole plane, and that of course will contain things that are not there in the original subspaces. So the span of Q and R is going to be bigger. So the span contains more elements. So again, there is no surprise here, right? But again, it's not really a disjunction. It's just the join in this particular structure. We can also look at the failure of distributivity. And again, this is the expression as we had before, but let's translate it into lattice operation. This sentence, this statement, basically means that X is in P intersection the closed span of Q and R. And this is not the same as saying that X is in the closed span of P intersect Q and P intersect R. Why is that? Well, if we take, let's say that P is this line here, and this is Q and this is R, the span of Q and R is the plane. So now the intersection of this plane with P is this whole line P, right? So we're saying that X is in this line. But if we do the intersection first, before the span, what's going to happen is that we have P, which is this, and Q, which is this line. The intersect is just going to be the origin. And again, P and R, the intersection is just going to be the origin. So we have the span of the origin. And so this closed subspace is just going to be the origin. And so again, the idea that intersecting with the span is not the same. There is more stuff there. And that's why the distributivity doesn't work. Like making the span is going to bring in more things. And so doing the intersection before and the span later is going to give you fewer things to reach. Okay, so we found that L is not a Boolean algebra, and so it has this failure, obviously, because these are the definition. And the point is like, okay, so what? So what? L is not a Boolean algebra. Well, the claim then is that the only relevant statements are those that are results of measurement, right? As we saw, those statements are the one connected with projective measurement. And since the lattice of closed subspaces contain all experimentally relevant statements because it contains all the results of the measurement, then quantum mechanics does not follow classical logic. Essentially, this is the claim. But this claim does not work because L does not contain all experimentally relevant statements. If it did, we would have a problem, but the thing is, it doesn't. So we can't really do everything that we want to do within L anyway. Okay, so we have to show that this is the case. First of all, the thing that we can say, that we can always say in general, is that probability theory requires classical logic. You can't do probability theory without doing classical logic. Why? Because the definition of a probability space is made by three things. An omega here, that is called a sample space, which is the set of all the possible outcomes, all the possible things that can happen. So if we have a die and we roll it, right, the idea is that there are only 6 possible outcomes, and we can label them as 1, 2, 3, 4, 5, and 6. Then, on top of the sample space, we have a sigma algebra, and the sigma algebra represents all the events that we can consider. So, for example, that the result is even, the result is odd, the result is less than 3, and so on. And note that any of these things can be understood as sets, as subsets of the sample space. Even means 2, 4, 6, odd means 1, 3, 5, less than 3 means 1, 2, 3. And so a sigma algebra is really a collection of subsets of the sample space. And then we have a probability measure, and a probability measure assigns the probability to each event. It doesn't assign probabilities to the outcomes, it assigns them to the event, to the sigma algebra. Why does it do that? And why can't we assign a probability to outcomes? Well, because that wouldn't work in the continuum. In the continuum, we have infinitely many cases, and if we want our probability to be additive, we would have either to assign 0 to each case, which means that the whole thing would be 0, or we would assign a finite number, but then we would have infinity for infinitely many cases. And so really the correct way of defining and thinking about probability spaces is that we need to assign events to the sigma algebra, to the sets, and not to the points of the sample space. Now, mathematically, a sigma algebra is a collection of subsets, as we saw before, that is closed under complement countable union, and countable intersection. And therefore, remember our connection between statements and subset, right? The sigma algebra is a countably complete Boolean algebra of statements. So it's a Boolean algebra. To define a probability space, we give probability to elements of a Boolean algebra. If we don't have the Boolean algebra, we have not defined a probability space. And so really the argument, it's like this. Probability theory requires classical logic because it requires a Boolean algebra. And quantum mechanics requires probability because it's a probabilistic theory. Like probability is really the core essence of quantum mechanics. It's how we describe things. And so quantum mechanics requires classical logic. So it's not even that we don't really need quantum logic, it's that we really, really need classical logic, otherwise we can't do anything. And the point here is that no subset of the lattice of the closed subspaces is a Boolean algebra. And therefore, L itself, the lattice of closed subspaces, is not sufficient for quantum mechanics. You really can't do everything that we need to do. Okay, so this is a very abstract mathematical argument, which of course is completely valid and completely general, but maybe it's better to go and take an example and really work the way through and see how really unreasonable is to think that quantum logic can actually be enough to describe all the things that we want to describe. So let's take the cases of the simplest cases that we can have in quantum mechanics, which is the case of a qubit. It's a two-dimensional vector space. And let's work out all the set of all the possible closed subspaces that we have and what do they correspond to physically. So in a qubit, you might know that all the states can be represented on what is called a block sphere. So essentially, every qubit is a direction, and this makes sense because the qubit is also used for a spin 1/2 system, and a spin 1/2 system is fully described by the direction of preparation. So we have a block sphere here, and now we want to write the Hasse diagram for the closed subspaces of a qubit, which represents all the statements that quantum logic can describe. So the first one is correspond to the zero subspace, the one with only the zero vector, and this corresponds to no states, and it corresponds to the empty set on the block sphere. Then we have the one-dimensional closed subspaces, which correspond to essentially every pure state, right? Every infinitely precise preparation. And so every one-dimensional subspace corresponds to one state, which is one point in the block sphere. And then the next level that we have, the two-dimensional subspace, is the whole Hilbert space, which would correspond to the set of all possible states, and therefore, in terms of the block sphere, would correspond to the whole surface, the whole sphere. So the only statements in quantum logic for a qubit are: the system is in no state, like the system doesn't exist. The system is in exactly one state, is in exactly psi, right? And the system is in some state. I don't know anything about anything, it's one of the states. And this tells us that in quantum logic, really, there are very few statements, almost nothing. There is nothing, one, and everything, right? And we can't really do much. Like, what are things, for example, that we would want to do? Well, we would like to create statements about expectation, expectation values, and probability, and statements out of uncertainty, and none of these are there in the lattice of quantum logic. So, for example, we might want to say that the expectation value of the spin in the z direction is 0. And this would correspond to all the states that are on the equator, right? All the states for which the component of z is 0. Well, that's not a set with only one element, and that's not the set with all the elements. So that set there is not a closed subset, it's not a statement in quantum logic. Or we might want to say that the spin is in the vertical direction plus or minus 5 degrees, because we never prepare or measure a pure state exactly with infinite precision. And so these are more typically the statements that we're going to actually use in practice. And this would correspond to sort of a small circle, on the top of the sphere. And again, this is not a set with only one element. This is not a set with all the elements. this is not a set in the lattice of quantum logic. So it's not a statement that is expressible in quantum logic. And another thing that we would want to do, that we can't do in quantum logic, is that we would like to distinguish between a different preparation. We might want to distinguish between, I prepared X plus or I prepared X minus. I prepared X plus or I prepared Y plus, or I prepared some state. Because in these three cases, right, if I knew this, right, if I knew that I prepared X plus or X minus, somebody else would be able to, with that knowledge, to essentially know precisely what was prepared, because you align the measurement in the X direction, and then you would know if I prepared X plus or X minus. If it's in these two cases, well, you can't really make a measurement between those two, but you can still create with a POVM a measurement to extract some information, some probability that I prepared one thing or the other. If this is really the only thing that somebody else would know, then you can't really extract anything from this information. And you see that all these three statements, right, correspond to the same thing here, because if I take X plus and X minus and I do an OR, I get, I do a join, I get the full thing. And the same thing with X plus and Y plus. If I do a join, I will get the whole space, right? So there is no way to distinguish between these three cases, which is important to distinguish between these three cases because I would be able to extract more information from the system. And again, we can't do this in quantum logic, and therefore, really, quantum logic does not have enough statements to be able to do everything that we want to do in quantum mechanics. Okay, so this is really the point. Like you can't do everything that you want in quantum logic. And somebody might say, okay, what should we use instead? Well, we use something that it's always there, that we already used in plenty of cases, which is the Borel sigma algebra, because every Hilbert space is an ordered vector space, which is a metric space, which is a topological space, and every topological space is equipped with the Borel sigma algebra. And this is what we actually use in practice. This sigma algebra is a Boolean algebra, and therefore it follows classical logic. It includes all the statements of quantum logic because the closed subspaces are Borel sets, so they're in there. It has a clear physical meaning that we have in our more general assumptions of physics project. I'm not going to talk about right now, but it can be given, so this is something meaningful. It includes statements of probability and expectation value, and it is what we use to define classical mixture in quantum states. So these are the things that we actually use to then extract the probability out of this. So it's what we use. It's classical logic. It's not something strange. As a last argument, sort of, I guess, nailing the coffin of this, is that given that quantum mechanics is probabilistic theory, we should really compare classical mechanics with the classical probabilistic theory version. And you can construct, and we're not really going to do it right now here. There is the paper, you can go and look at how it's done. But the point is that you can construct a parallel where you create a lattice of subspaces where these are going to be probability distribution over phase space. And therefore, you are going to have a lattice of closed subspaces even for classical mechanics. And then, of course, also that will violate the disjunction, will violate the distributivity, and therefore you can, of course, conclude that classical mechanics violates classical logic and it requires quantum logic and so on. And whether this lattice of closed subspaces in classical mechanics is as useful as the one in quantum mechanics is sort of beyond the point. The point is that this mathematical structure exists and you can make similar arguments. And so it kind of doesn't make sense to think that either classical or quantum mechanics really require this structure as the fundamental logical structure. So, okay, what's the point? Is that quantum logic as a mathematical structure exists and you can do computation of it, and some people find it useful for doing some things, and so that's fine. And this is the lattice of closed subspaces of the Hilbert space, which is defined not just for quantum mechanics, but also for classical mechanics or any any theory that you want to have that has Hilbert spaces, or even groups. Even for groups you can construct these things. But the point is that it's neither quantum, because it exists for a bunch of other things. It is not either a logic, because it does not contain all the statements that are required in quantum mechanics to be able to describe the thing that we need to describe. So this leads us to our conclusion, is that there is no such thing as quantum logic. There is just a lattice of closed subspaces of a Hilbert space. That's it. So what did we learn? Well, first of all, if you're still here, you learned that you really want to know the details about this. And, that's good for you. I mean, I really think that the main problem on the foundations of physics and foundation of quantum mechanics is really people taking sound bites and repeating it without a real proper understanding of what they're talking about. And this sort of generates this never-ending confusion, which I have no hope that we can go out of. But yeah, so, at least that's really the right way, going and look at the details. Second, I hope it should be obvious that, again, quantum mechanics and classical mechanics are not that different. If you set up the parallel correctly, like we do in our project or we did in other videos, you find that they're not that different. In fact, you can learn a lot from one to the other. There are a lot of things that are transferable, and there is some tuition that are better understood in quantum mechanics and others that are better understood in classical mechanics and so on. So they really complement each other in terms of understanding. And then the last point is that I think this confusion about measurement and what is the correct algebra of logical statements for measurement is really shows that we don't even have a commonly accepted framework for describing how what is the correct logic of experimental verification and so on. And this is something that is dear to me, because in our project, Assumptions of Physics, we actually try to do that. We have a notion of experimentally verifiable statements, and then this map very nicely to topologies, and then the sigma algebra that we talked about before, they really correspond to statements that are associated to an experimental test. So when we're talking about assigning probability to a sigma algebra, really conceptually, we're assigning probability to statements that have, at least in line of principle, at least in the theory, an experimental test associated with it. And I think this is really the problem. We need a mapping between the math and the physics such that we can be mathematically precise, but we are also physically precise, and we are not losing. We have a real clear physical meaning for those mathematical objects. And this is actually what we try to do in our project as Assumptions of Physics. So if you're interested in these things, and if you also think that this is the problem that we have, you can watch my video, follow our project, and that's it for now. See you in the next video.